And for the latter scenario, we find that the mean AMOC tipping time estimates of our ensemble, that was 2055. So that is in the second part of the century, so which is like in 30 years from now. So that is quite close by. I was really surprised by this result.
In this ClimateGenn episode, I speak with Dr. René van Westen about his recently published papers with his colleagues that identify a physics-based method for forecasting the very consequential AMOC tipping point. If or when the AMOC, full name Atlantic Meridional Overturning Circulation, collapses, it will lead to Northwest Europe plunging into freezing conditions with an estimated 20% less rainfall and widespread societal disruption, especially to food production and energy needs. In René's own words,
there is this signal that this may be a potential scenario which we can't ignore because the impacts are quite drastic, and therefore it is very worthwhile to know what we can expect as a society. And I hope in the end that I'm wrong also in the predictions, because we don't want to deal with these kind of changes, because that's in the end very difficult to adapt to.
In the next episode, I am speaking with Professor Paul Behrens, who is the British Academy Global Professor at the Oxford Martin School at the University of Oxford. Paul specialises in exploring the intersections of climate, energy and food systems, suggesting one proven action that we can all take that could change our course from famine to one of better health and more abundant and affordable food supply. Paul Behrens is also the keynote speaker at next week's Sustainability and Drinks Conference in London, where I will also be chairing the high-level panel at the end of the session. If you are in London and work in any aspect of the drinks business, then do consider coming along. Tickets are available from the SID website. Thank you very much. René, it's great to see you again. Thank you very much for taking the time. Your recent paper shows that your research is kind of developing into an indicator for the onset of an AMOC tipping event. And there's been a lot of discussion around tipping point indicators and why we need them and so on. What are the characteristics that you look for that constitute a tipping signal?
So with this new paper, which was published last August, we were aiming to develop this physics-based indicator. And this is important that we use a physics-based indicator because they are more robust in terms of prediction, because you know the underlying physics, the mechanisms that cause eventually the AMOC tipping. And that was the main aim, because in the end, what is a very big problem with these AMOC projections is that the AMOC can tip, but that takes place beyond 2100. So you need these very, very long simulations, which are not always available. And we thought, so maybe you already surpassed like a critical range or a critical value for which your AMOC eventually does collapse, but you simply turn off your simulations. But if you would continue them, you would see that the AMOC indeed further declines beyond 2100. And therefore, we were exploring okay, can we develop such an indicator? And this is also very important, because then we can effectively communicate with people, like this may be a potential scenario under that kind of emission scenario.
What are the kinds of things you're measuring within all of that are giving you the data that's telling you?
I think that the first time we spoke, we discussed that, the other paper, which was published in February 2024. And we also had a physics-based indicator. So this first indicator, that was the amount of salinity or fresh water that was important into the Atlantic Ocean by the AMOC at 34 South. This indicator only works when you apply a forcing that is very, very slow, like in a very gradual manner. And in that case, this one is the most accurate indicator to use. However, the present-day AMOC is forced under climate change, which is a very, very rapid forcing. So that means that this indicator about the salinity transport at 34 South, it simply breaks down. We also showed it in the paper. It doesn't work. You don't get any reliable answer for that, because there is an assumption to use this indicator, you need these very slow conditions. So therefore, we need to look at a different kind of property of the AMOC, and that is how much water sinks in the North Atlantic Ocean to the deep sea. So that is the conveyor image. So water is flowing northward at the surface, then it sinks and eventually returns as a cold, deep undercurrent, and it flows out of the Atlantic Ocean again. And this sinking component, that is a very crucial part of the AMOC as well. And actually, these new indicators, they actually represent how much sinking can take place. And this is also connected with modern AMOC theory.
I remember when we did first talk, we were talking about how you loaded the model with water to simulate this abrupt collapse. Now, how likely is that scenario?
So that first scenario we presented with adding a lot of fresh water, that's not very likely because we eventually have like 80 times the amount of Greenland ice sheet melt rate, which is like a ridiculous amount. And also people are read it in blogs, they also select like, oh, you can't take this study serious because they are adding so much Greenland ice sheet. I think in the end, we are adding like 5 times the entire volume of Greenland to the Atlantic Ocean. So that is an absurd amount. But that was not the aim of the study. We were just seeing whether we can collapse the AMOC under a very slowly increasing freshwater flux forcing. So that was more of a sensitivity experiment. And we learned tons of that, like when does the AMOC collapse? What are the different physical mechanisms operating which govern the AMOC collapse? How quickly does a collapse occur? And this is like a very nice isolated experiment because now we know like how a typical AMOC tipping event takes place in such a climate model. And now we can use that knowledge and look how it operates under climate change. And there it becomes quite different because there are like these dynamics that also takes place, but you also get like a temperature forcing on top of that. So it becomes much more diluted. And without the knowledge of this first experiment, it is very hard to explain what's going on under a climate change scenario. And now we can actually do and separate them and see like, hey, this is the part we can attribute to climate change, and that is the part which we can attribute to the destabilizing feedbacks that eventually cause the AMOC to collapse.
Establishing that, can you now give us a more realistic timeline and the characteristics of what this starts with?
How we started the study is that we first did analyze this water loading simulation because that one is the most pure one. And there we could demonstrate like, hey, this indicator, this sinking that can take place, that can shut down. And what we saw is that there is some kind of heat loss towards the atmosphere. So the water in the end needs to get denser in the Atlantic Ocean. And eventually when you add, for example, too much fresh water, this densification of water that can stop eventually, and that meaning that there's no sinking anymore. And actually that means that the AMOC needs to shut down. So that works very, very well in this idealized experiment. And then we check this, whether it also worked under climate change. Because then you're heating the atmosphere due to enhanced greenhouse gas emissions. And this additional heat in the atmosphere, this causes less heat release from the ocean to the atmosphere. And that causes also like some kind of AMOC weakening that is due to climate change. So first you get an initial AMOC weakening. And if your AMOC weakening is strong enough, then it can also cause this destabilizing feedback to take over. So there are like first a initial phase, which you get an AMOC weakening due to higher temperatures in the atmosphere and in the ocean. And if your AMOC is weak enough, then you can also trigger this destabilizing feedback. And that causes your AMOC start to dwindle down almost to zero. And we did that with our experiments, but they were always tweaked. So we had like a background hosing forcing. So that is, of course, not very realistic, that we're still like adding 25 times the amount of melt rate of the Greenland ice sheet. Also to tune our model a little bit to get it in a more sensitivity regime. But what we have actually showed that in our model, this indicator works under different kind of scenarios. It works both on hosing simulations, that's adding fresh water, but it also works under those climate change simulations. And then it's the final step is, okay, how does it then work in the latest state-of-the-art climate models? So we took all different kind of climate models, which were participating in the latest IPCC report. So those are the so-called CMIP6 models. And we took 25 of them and just looked at what the mean statistics are of this ensemble. And it turns out that this indicator, it also works under all those different kind of climate model simulations. And what is most important, that we have like a certain kind of threshold. We have this indicator when it switches sign, so going from negative to positive, it indicates when the AMOC is likely to collapse. And then we can actually look at which year does this correspond, and also to which or the level of global warming when this certain value is surpassed.
I know there are sort of different scenarios based on different emissions. What's the deciding factor with these emission scenarios? Can you just elucidate a bit of that?
In the end, so you have different kind of emission scenarios, and like to around 2040, they don't differ that much. So they all show the same kind of warming. And then after 2040, you see really that their emission paths start to differ. And also that's also reflected in the global mean surface temperature anomaly. So the lowest emission scenario that is already then stabilizing. It becomes like stable around 2050, and then also temperatures sometimes also decline in the second part of the century. And then you have the intermediate scenario for which temperature increases to about 2.5 to 3 degrees warming. And then we have the very high emission scenario where you see like 5-degree warming beyond 2050. That was quite interesting because in the end we did a intermediate emission scenario. So to be exact, this is the SSP 2 4.5, and we did a high-end scenario, the SSP 5 8.5. And for the latter scenario, we find that the mean AMOC tipping time estimate of our ensemble, that was 2055. So that is in the second part of the century, so which is like in 30 years from now. So that is quite close by. I was really surprised by this result to find that this was what the ensemble told us, the ensemble mean. But if you then look to a lower emission scenario, they don't differ that much, like from 2050 yet. So of course you're having a lower warming in that other path, but still it is not deviating that much. And hence we also find that the mean tipping time estimate for the intermediate scenario was quite close by. It was in 2063. So only a few years later compared to the high emission scenario. I should say that the amount of variability, especially in the lower emission scenario, it spreads more substantially compared to the high emission scenario. So if you take, for example, what is the risk of AMOC tipping in this ensemble by 2100, it is 88% for the high emission scenario, but it is only 57% for the intermediate scenario. So there you see a quite substantial difference, but not so much in the mean.
There seems to be a sort of inevitability in terms of the emissions being where they are and so on. And I was reading a press release from, I think it was from the Potsdam Institute last week, where they mentioned 4 tipping points that were tipping. And they mentioned AMOC, they mentioned South America, Amazon, and Greenland. Is there any research that looks at how something like Greenland tipping could overtake the human contribution?
That's a really good question. And at the moment, it is very hard to assess that, because in those climate models, they are not perfect. And the Greenland ice sheet is usually prescribed, which just means that there's like a very big block of ice sitting in the climate model. And although you're increasing like your temperatures to like 8 degrees warming or like 20 degrees warming, the Greenland ice sheet doesn't melt. And why we do this, like on very short time scales, like until 2100, of course, the Greenland ice sheet is melting, but it is not changing that much in terms of topography, also size. Of course, Greenland is melting definitely for sure. And there are now the first models which are available that have like an interactive ice sheet. So it is mainly computational limitations at the moment that we can't have like this coupled version in which the Greenland ice sheet really melts in the ice sheet, in the global climate model. But with increasing computational power, eventually we will see these fully coupled climate models like that. Also the Greenland ice sheet can melt, and then you can actually measure how much water from Greenland is getting poured into the Atlantic Ocean. And then you're having also those beautiful feedback mechanisms that can play a major role. That will be very interesting. And then that will be the next step forward also in this field.
Is that where you're going with this research, in this sort of much more sort of dynamic interconnections? So to speak?
Yeah, so in the end, that is very crucial. And there was also this a colleague of mine that also looked at a very simplistic kind of box models. So they have like an West Antarctic ice sheet, an AMOC, and the Greenland ice sheet. So like three different kind of models. They were coupled. And then you can all find different kind of interesting behavior. At first, the Greenland ice sheet starts to melt, which collapses the AMOC, which then also causes a collapse of the West Antarctic ice sheet, and then that revives the AMOC again. So you're getting these different kind of intriguing mechanisms, but it really depends on the magnitude of the couplings, but also how fast and the delay in that kind of sense. So it becomes so complex, and then you're getting like this cascading and interconnecting tipping elements that they are just communicating with each other, and we can do so with simple play and toy box models. But yeah, much more needs to be learned from that.
In terms of this interacting between tipping points, do you think, I'm just anticipating as you probably haven't done this research yet, but do you think that this changes that timeline?
So that could be that we overlooked some stabilizing feedbacks in the climate system. That can potentially be the case. But if you only look, for example, at the Greenland ice sheet and the AMOC as like the two main tipping elements that may already cross the threshold in the upcoming decades. So if the Greenland ice sheet starts to melt, it destabilizes the AMOC. So that is quite certain. So if you take, for example, those estimates we had, so probably if you would consider also this additional contribution of the Greenland ice sheet, I would suggest that the years we label, for example, this 2055 under the high emission scenario, that it can become even earlier, because that coupling is now not simulated within this climate model simulations. But of course, we also miss other kind of feedback mechanisms. So it's very hard to tell what will the eventual year be. Is this now earlier or later? There is a lot of uncertainty around that. So we can't quantify that. So for now, we have this kind of first estimate. And that also nicely fits with the drive-out study, which was also published in August. That really showed, like, if you continue your simulations beyond 2100, you see that most of them under the high emission scenario, they eventually will show a full AMOC collapse.
Just to give it some context, we always think of Northwest Europe as being in the sort of the eye of the storm here. Talk about, as a reminder, some of the tangible impacts that we would experience.
So we have now a few studies, one published, one currently under review, and there's also one which we're planning to submit, and that addresses like all different kind of climate impacts under a collapsing AMOC using our climate model simulation. So this was specifically done for the Community Earth System model. So we've analyzed the temperature extreme impacts for Northwestern Europe, what is happening with precipitation and droughts, and the one that is currently almost ready for submission. And of course, it needs to undergo the full peer review process. That is on sea level rise, additional sea level rise. And what we saw for Northwestern Europe, if you look at temperature first, is that you have like very cold winter extremes. So temperatures can drop substantially, especially the cold extremes. So if you take parts of Northwestern Europe, for example, big cities such as London, you can see that the cold temperature extreme can drop by 15 degrees Celsius. And there's then a combination of climate change, like an intermediate climate change simulation in combination with a collapsed AMOC. And that is, of course, quite spectacular. And you also see the northern countries such as Norway or Sweden, they have very spectacular temperatures, cold extremes like minus 40, which are reaching almost south of Norway, but also over Sweden. So those temperature responses can be quite spectacular. And also this temperature contrast now between Northern Europe and Southern Europe that also strongly amplifies cyclone genesis. So winter storms are getting much more intense. So that you get a combination of very cold winters in your northwestern part of Europe, and that can be followed by warmer summers, even hotter extremes. So in the end, the seasonality strongly increases, which is most pronounced for the winter months. So that's one part. So the second part is precipitation. And what we actually see is that the overall precipitation on a yearly basis declines by about 20% over Europe. So that is quite a robust signal. It's also showing up in other climate models. So not with the SESM, so our model, but also in EC Earth. And also in very old kind of climate models, this is a very persistent signal we see in different kind of climate models. And that also in combination sometimes with warmer summer temperatures, which results in more evaporation. So you get on one hand, you receive less precipitation, but you also have higher evaporation over the land, which means that your droughts mainly increase. So a greater frequency in those. And finally, we have also an increase in your dynamical sea level. So that is also increasing due to an AMOC collapse. So the surface of the ocean is not flat. There are all these different kind of bumps. So like kind of low pressure, high pressure areas. And currently, this dynamical sea level is actually lower than what you would expect. And that is due to the influence of the AMOC. And if the AMOC shuts down, we're actually adding a lot of surface water to the North Atlantic Ocean. So this slope actually just reverses. And this causes about 50 centimeter of additional sea level rise in the North Atlantic Ocean. And this latter result, we analyzed this in much more detail in the paper, but it was already presented in our 2024 study, where we actually showed that the dynamical sea level is increasing. And this was also addressed by studies from 20 years ago. They also did this first analysis. But now we actually also look at the timing, how fast the rates are. So a much more detailed kind of view of how a abrupt AMOC collapse causes dynamical sea level rise. And all those three are quite interesting for society, but also for policymakers, because it can really change, of course, your whole narrative. What do we need to know for the future, right? Colder winters, even more drought, or higher sea levels, etc.
I've asked you this before, but have you, since I last asked you, had any interest or traction with policymakers at any level?
Our Dutch government, they have, of course, all different kind of departments. And they contacted me, so I gave a few interviews. And I also saw that Wopke Hoekstra, so from the European Commission, they also posted on our study on LinkedIn. So he made a post. So it is somewhere also maybe sometimes beneath the surface that people are, considering this as a potential scenario. And they are, of course, very interested what the impacts are. And I hope that our studies give like a first initial thought, or a first initial picture. Hey, this is a scenario. But it is very interesting that other studies with different kind of climate models do the same kind of analysis to show whether our results are maybe like overestimated. For example, for the temperature extremes, we know that there are a few biases, especially in the sea ice. So therefore, it is very important to have a better picture. What is now the model spread? What are the extremes we can expect, for example, beyond 2100? Those are very important questions that we need to address as scientists and also to inform policymakers, but also the public.
Given how much you've focused on this so far, and I've interviewed you 3 or 4 times, and is this now becoming something that you're ongoingly developing, and you're going to be staying involved with and making it a core of your own work?
I hope so, or at least for the moment. I'm really enjoying. Also, sometimes I'm a little bit also getting worried about the impacts and the results as well. But this is a really fascinating topic from a pure physics point of view, like that such a large-scale ocean circulation can induce these kind of climate effects and impacts on society as well. And we have a unique set of climate model simulations, and we can learn a lot of new aspects from the climate, how it operates under different kind of AMOC strengths. And this is very worthwhile to investigate further. And there's also ongoing collaborations with scientists beyond my field. So I'm more of a physical oceanographer, but I've now also worked with temperature extremes, precipitation, dynamical sea level. Of course, that is somewhat related to physical oceanography. But there's also now a new collaboration which delves into the tropical cyclones, whether they are the hurricanes over the Atlantic Ocean, whether they are affected under an AMOC collapse. So a lot of to be explored and to see these different kind of connections maybe showing up.
This is really just to end on. I mean, but you wear the sort of oceanographer, the physics side of it, the scientist hat, and then you're talking about trying to engage policymakers of what the world could look like. And I know that you're a parent as well. You're wearing all these different things. When you put all these together, when you step back, is it that something you think, this is really consequential for society that we really get into this? How do you find that side of it when you step back and try and sort of place this in societal discourse, if you like?
It's like physicists and myself, we just sometimes report numbers And then it's like, oh, this is like a massive decline in temperatures or a huge increase in dynamical sea level. And and especially also with me, I'm like, oh, that's very fascinating. And then there's like, okay, continue next. But if you take a step back, and then I'm really worrying from a citizenship point of view and also from a member of society, I'm like, wow, that is really spectacular. And I'm not sure how well we can adapt to this. And that also sometimes makes me worry whether, because at the moment with our latest study, we have this date. Of course, you can criticize that because we use climate models, etc. They are not fit for purpose, etc. And yes, but now there is this signal that this may be a potential scenario which we can't ignore because the impacts are quite drastic. And therefore, it is very worthwhile to know to what we can expect as a society. And I hope in the end that I'm wrong also in the predictions, because we don't want to deal with these kind of changes, because that's in the end will be very difficult to adapt to. And that's also what we see nowadays with current climate change, in which temperatures are rising over the past few decades, and of course also before that. It is also really difficult now to fight climate change and to adapt to rising temperatures. We see it with old buildings, and that is already causing a massive amount of inventive and adaptations you need to consider. And that makes it already quite complex that the current climate is warming at that pace. And now imagine that we are, for example, cooling at an even larger pace. I think it will be very hard for society to adapt to. And yes, I'm not a expert in adaptation, but I can imagine that it will be quite challenging for society, and therefore I'm also a little bit worried. And we try to come up with better estimates, because in the end that really also helps policymakers, but also people on the adaptation side, to make these very accurate projections for the nearby future.
Well, that's the key, isn't it? Is arming policymakers and society with the tools to try and make better decisions. And so far we haven't been very good at it, but hopefully we'll get better. So look, thank you very much, and let's speak again when you publish more work. It's always really interesting. Really appreciate it.
Yes, you're welcome.
If you are concerned about the future, then why not travel with me through every COP conference from COP21 in Paris to COP28 in Dubai by ordering my book COP Out: How Governments Have Failed the People on Climate. In COP Out, you'll gain insights into what is actually going on in these supposed world-saving conferences, and how we have ended up in this dire era of dangerous consequences. You can order COP Out via the link in the notes or on any online bookstore worldwide in paperback or audio version.